All right, online class, let's get ready for test 2. So what we're going to begin to look at, I'm on the wrong page, let's go up to page 1 here, and I'm going to run through the types of problems that you need to be ready to do for your upcoming test 2. The very first thing that I always do, first of all, this test is totally non-calculator. It's just one part, no calculator needed for anything. And the first thing that you always got to do on this is fill out the unit circle. Okay, so I'm going to review how you do this. This is the only test that I do this on, but you have to be able to fill out all of the points on the unit circle, and you got to be able to fill all of the radian measures of all the angles out too. So let's start with all of the sides, or not the sides, the points. Okay, so first of all, I like to look at this point right here, which is a 0.10. We do have a unit circle, so we know that the radius of this circle, of course, is 1 unit. So that distance from there to there is 1 all the way around that circle. So that would generate this point, which has a 0 value for x and 1. This point is -1, 0. This point, 0, -1. So I always start there. Now, what I like to show students how to do is just fill out these points right here. And let's go like this. Now, when I look at these 3 points, and if you can get these 3 points right here figured out, the rest is very easy to finish up. Just by some basic knowledge of how points work on a coordinate system. So I look at these x values as getting bigger. Okay, from here to here, the x values are getting bigger. So I'm going to put just a 1, 2, 3. They're getting bigger. Now, the y values are getting bigger this way. So for my y values, I'm going to go 1, 2, 3, like that. So it's real simple to remember how that goes. And it's very logical. Okay, now we need to do a little bit more with that, obviously, but just remember how those points go. Now, the next thing you do is you do a square root of all of those numerators, except 1. Don't waste your time with 1, because after all, the square root of 1 is 1. And then divide everything by 2. Okay, so there you have your points, just like that. Very logical, very easy to derive. Then what you do is this. So if you just move this point over here, what's going to happen is the x value is going to change. So that's going to be, all these x values over here are going to be negative. So it's just going to go -1/2, -√2/2, and -√3/2, while the y values stay the same. So this is going to go 1/2, √2/2. See, the y values are getting bigger as we go up, like that. Okay, so that takes care of that. Now, let's do this. Let's reflect these points. If we reflect these points over the x-axis, what changes? The y value changes. So now when we go to this quadrant, all of the y's are negative. Everything else stays the same. So this is -1/2. Reflect this point. That is -√2/2. Reflect this point. That is -√3/2. Then the x values stay the same. So this is, this point right here comes straight down. That's going to be √3/2. This is going to be √2/2. And that's going to be 1/2. Okay? Now these points are going to get reflected over this axis. So the only thing that's going to change from this point to this point is the x's are going to be negative. Okay? When we reflect those. Okay? And everything else is going to stay the same. So this point just becomes -√3/2, -1/2. This point, when you reflect it, becomes -√2/2, -√2/2. Then this point becomes -1/2 and -√3/2, like that. So all the points are done. Now we just got to consider the angles, okay? Now the angles also have patterns on it. So one of the things I like students to be able to do is you don't need to work with degrees and change them to radians. All you need to do is just kind of go around the circle and get this all put together like this. So I'm going to do these maybe like in red. So that's 0 radians like this. Now what I'm going to do is I'm going to start by counting on this just by this increment right here. Of course, that's 45 degrees right there. And 45 degrees is the same thing as pi over 4. If you don't remember that, you can convert it so you get pi over 4. And what I'm going to do is I'm just going to start counting by this. I'm going to go 1 pi over 4. So that's going to go there. Then I'm going to go 2 pi over 4. But 2 pi over 4 reduces to pi over 2. Okay. Then we're going to go to 3 pi over 4. I'm just going by 45-degree increments. So this is going to be 3 pi over 4. Then I'm going to go to 4 pi over 4, which of course 4's cross out, leaving pi. Keep going. 5 pi over 4 goes here. Keep going. 6 pi over 4 actually reduces to 3 pi over 2. Keep going. 7 pi over 4. Okay, and you could go one more time and you would get, of course, 8 pi over 4. And then 8 pi over 4 is just 2 pi. Okay, so we got that. So what I've done is I've went around the circle and I counted off by 45 degrees. That's why I'm going to kind of do this in a different color like that. So we count by pi over 4. That's all you got to do. Now the rest of this is we're going to count by 30s. Okay, so if we look at this angle right here is 30 degrees. And 30 degrees, if you don't remember that, you could convert it by doing this. That's pi over 6. So what we're going to do is we're going to count by pi over 6 the same way. So pi over 6 goes here. Remember, we're going by 30 degrees. So you're not going to pay attention to these, this angle right here. Don't go to that. Go to the 60-degree angle. So just count off by it. 2 pi over 6. Now that's going to reduce to pi over 3. Okay, then keep going. Then go to 3 pi over 6. Well, that's pi over 2. We already have it. Keep going. 4 pi over 6. That actually reduces down if you do that to 2 pi over 3. So that goes there. Keep going. 5 pi over 6. Okay, that goes here. Okay, 6 pi over 6. 6 pi over 6 takes you back to pi, which of course we already have. Keep going. 7 pi over 6. That goes here. Keep going. 8 pi over 6. Reduce that to 4 pi over 3. Okay, keep going. 9 pi over 6. 9 pi over 6 is really 3 pi over 2. We already have it. Keep going. 10 pi over 6. That reduces to 5 pi over 3. And then one more time, we're going to go 11 pi over 6. So we're here. And just to make sure you're counting okay, go one more time. 12 pi over 6 is 2 pi. So we have made it all the way around the circle. Now, that's how you do it. You don't have to memorize stuff, although you can. You can count them out. And one of the things that I always kind of tell students, there's really nice patterns in the denominators. If you've never paid attention to this, look at how the denominators go. 3, 4, 6. 3, 4, 6. Isn't that beautiful? And look at this. 3, 4, 6. 3, 4, 6. So you can also, kind of look at things like that. It's full of patterns, so that's the idea. Okay. Now what we're going to do on this now is usually I have you fill out a unit circle, and the other thing I have you do primarily is to go through and just fill out some trig functions on this. So if I wanted you to find the sine of 11 pi over 6 on a unit circle, you're looking for the y value. So 11 pi over 6 is here. So that y value is negative 1/2. That's all you got to do. Then if you look at a cosine, okay, you're looking at the x value. So locate 5 pi over 4, which is here, and locate the x value. So that is negative square root of 2 over 2 like that. Okay. Now if you're going to do a secant, okay, a secant on a unit circle is, remember the definition is r over x, but on a unit circle it's really just 1 over x. It's really just going to be the reciprocal of the cosine. So if you were to go to negative pi is clockwise. Your x value is what matters. You want to do the reciprocal of that value. So you just do 1 over negative 1. So you get negative 1. And that's how you do that. Okay, now you go to the tangent. When you're doing a tangent, you're looking at y over x. So you got to figure out what negative 330 is. Of course, that's a clockwise angle and it goes all the way to there. You're going to have 30 degrees C left over like that. So you're looking at this point right here. So what you're going to do is you're going to do y, which is 1/2, and you're going to divide that by the square root of 3 over 2 and work out the details. So that's going to be 1/2 times 2 over root 3, crosses out, that's 1 over root 3, and then you can rationalize that denominator to get square root of 3 over 3. So basically, if you know you want to be sure that you know the definitions of your trig functions. And remember, when you're dealing with the unit circle, it's a little simpler. The sine is just the y value, the cosine is just the x value. The secant would be the reciprocal of the cosine. The cosecant would be the reciprocal of the sine. Then the tangent, of course, you got to do y over x. And then the cotangent, you'd have to do x over y. So that's a typical kind of problem. You fill out the unit circle, and then answer questions based on that. Okay, that's the idea. Okay, next page, going to get a little bit into identities. There's only certain identities that I'm going to give you. I'll discuss that as I go through this. This one right here is going to say find the cosine of negative 15. I'm pretty sure this was supposed to say use the cosine sum identity. So what we're going to do is we're going to write the negative 15. If I want you to use a sum or difference identities, these identities go like this. The cosine of alpha plus beta, you have to memorize this, goes like this. It goes cosine alpha, cosine beta, different sign, then it goes sine alpha, sine beta. So I always try to get students to memorize this way. Cosine of alpha plus beta, you go cosine, cosine, sine, sine, different sign. So if it's plus, that's minus. Then if you have a cosine of alpha minus beta, it goes like this. So it's going to be cosine alpha, cosine beta, plus sine alpha, sine beta. Okay, like that. So we'll go ahead and work this out. First thing you got to do is figure out two angles that subtract to give negative 15. There's more than one way to do this. I'm going to work with 30 degrees minus 45 degrees. You could also work with 45 minus 60. You'll get exactly the same answer. So the identity goes like this. We go the cosine of 30 times the cosine of 45. Different sign now, so if that's minus, do a plus. And then do the sine of 30 degrees times the sine of 45 degrees. And we need to just go to the unit circle to figure this out. So if you could go back to your unit circle and problem 1 if you wanted to, or you can just do like I do. I just sort of create what I need as I go. So what I'm going to do is just at the side here, going to look at what I need. I need the cosine of 30, and I need the sine of 30. So I'm going to do this. I'm just going to draw in quadrant 1 of a unit circle, there's 3 key points. There's 30, 45, and 60. And the point on 30 goes like this. The x value is as big as it can be, so this is going 1, 2, 3. So that's square root of 3 over 2. The y values are getting bigger, so 1, 2, 3. So that's 1/2. And then this point right here is going to be, for 45, is going to be square root of 2 over 2, square root of 2 over 2, like that. All right, so if I do the cosine of 30, well, then that is the x value. So that's going to be square root of 3 over 2. If I do the cosine of 45 degrees, that's the x value of that. So that's going to be square root of 2 over 2. Plus, now if I go to the sine of 30, that's the y value, so that's 1/2. And then the sine of 45 is this y value, so it's going to be square root of 2 over 2 like this. All right, so this is going to be square root of 6 over 4 plus square root of 2 over 4. Add that together. The final answer is going to be square root of 2 plus square root of 6 over square root of 2 over 4 would be your final answer to that problem then, like that. Okay? And one thing I want you to notice on this, if you're dealing with the cosine of negative 15, that's in quadrant 4, and the cosine is positive, so that's reflected by that answer. We got a positive answer. So it's good to think about things like that. Okay, the next problem is finding the cosine of 22.5. Okay, and this one you're going to have to use a half angle identity on. So I do give you the half angle identity. So the half angle identity, basically goes like this. If you're dealing with the sine of alpha over 2, again, I'll give this to you. If you have it memorized, it does speed you up a little bit. It goes 1 minus cosine of alpha over 2. So when we're working with this identity, the first thing that you got to do is you got to write the sine of 22 over 5. You got to double that angle so you get the sine of 45 degrees over 2. You have to start it that way. And see, in this identity, alpha represents not the 22.5, but it represents the 45. It's what's being cut in half. So then when you put this in, first of all, 22.5 is in quadrant 1, which is going to tell you that the answer to the sine of a quadrant 1 angle is positive. So you have to figure that sine out that way. All right? So this is going to basically give us then positive square root of 1 minus the cosine of 45 degrees all over 2. Okay, and then we just work it out. The cosine of 45 is the x value, so you can go back to this unit circle. That is square root of 2 over 2. So you're going to have the square root of 1 minus the square root of 2 over 2 all over 2. And then we need to get rid of that fraction. So underneath the radical, if we multiply the top and bottom by 2, then we will have eliminated that radical. So, or not the radical, the complex fraction. So 2 times 1, you're going to have your square root. 2 times 1 is 2. Then you got to multiply this by this. That's going to cross that out, leaving root 2. And then the bottom is 2 times 4, so you have that. Now, you can do this in your head if you want to. What you really have is the square root of 2 minus square root of 2. And then you can do the square root of 4 as 2. So then this would be the final answer to that problem, okay? And you can leave it like that. You can have a radical under a radical. Okay, next problem, it just says simplify the expression. So what you'd have to know on this is you'd have to know the appropriate identity. Again, you have to know the sum and difference identity, so let me review those. If you have the tangent of the difference of 2 angles, that goes like this. It goes tangent of alpha minus tangent of beta. See, that sign matches that, minus, minus. Then it's all over 1 with a different sign, and then it's the product of those two. So it's got a nice structure that's pretty easy to remember. And then if you're doing the tangent of alpha plus beta, very similar. The numerator is tangent of alpha plus tangent of beta. And then the denominator is 1 minus tangent alpha, tangent beta. So study the structure of those things. The thing that you want to notice is if that's minus, that's minus. If this is plus, this is plus. And then I think then these signs right here are different. See, so minus, plus, plus, minus, like that. Okay. So structurally on this problem, if you're doing the tangent of beta minus pi, you need to plug into the difference identity, which is this one. So what you're going to say is the tangent of beta minus the tangent of pi all over 1 plus the product of tangent beta times the tangent of pi. Like that. Okay? So now, what we need to do is just figure out what the tangent of pi is. Okay, so you can look at a unit circle on that and figure that out if you want to. Okay, so I'm just going to draw a little diagram over at the side. Okay, at pi radians, what matters is we're at the point -1, 0. And the tangent's y over x, so that would be 0 over -1, or that would be 0. So the tangent of pi is going to be 0. So we work it out like this. We're going to have tangent of beta minus 0 over 1 plus tangent of beta times 0. So the numerator is tangent of beta. Denominator is 1 plus 0. So you get tangent of beta over 1. Or the answer is going to be tangent of beta. Okay, so yeah, it's just knowledge of the identity and showing that you know how to use that identity. Okay, on the next page, these problems all go together when you're doing this. So what I've done on this particular problem is I've given you, first of all, I've given you the tangent of alpha is given as -3/5, and that angle alpha is in quadrant 4. So one thing I'm going to do on this is we're going to find the sine of 2 alpha, cosine 2 alpha, and tangent of 2 alpha using this identity. Okay, so I'm going to draw a picture over at the side here, like this, and let's just kind of draw a quadrant 4 angle of some sort, just arbitrarily. That's angle alpha, which is going to be located in quadrant 4. And what you're given on this, if you're given this information, you're given that the tangent of alpha is equal to negative 3 over 5. And remember, the definition of the tangent is y over x. So if you wanted to go through and draw like a reference triangle for this, okay, that should have been y. I said y, but I didn't write it. So y would be represented by this piece of your triangle, and x would be represented by this. Okay, our job, of course, would be to figure out what r is. That's pretty simple. That's just Pythagorean theorem. So we're going to go x squared plus y squared equals r squared. So that's going to be 25 plus 9 equals r squared. So that's 34 equals r squared. Square root both sides, and of course you're going to get a positive answer. So you have that. Okay, that's all we need to know then. All right, so if we're going to do the sine of 2 alpha, I also do give you guys the different identities for the double angle identities. I do think those are nice to know, but I do give those to you on this test. You're going to have a lot of identities you're going to have to remember. So this is sine of 2 alpha is going to be 2 sine alpha cosine alpha. All right, so if we do the sine of alpha now, we just need to go to our diagram, and you got y over r. Okay, so we're going to plug that in, and that's going to give negative 3 over the square root of 34. Then if we want to find the cosine of alpha, we do x over r. Okay, and record that. So that's going to be 5 over the square root of 34, and then you just multiply this out. So going straight across, you're going to have 6. Negative 6 times 5 is negative 30. You're really doing a square. You're doing the square root of 34 squared, which is 34. And then you can reduce this fraction. Do it in your head if you want to. You're just dividing by 2 over 2 to get an answer of negative 15 over 17. Okay, which makes sense. Okay, so you've got, based on this diagram, you got negative 15 over 17. Okay, now we're going to go to the cosine identity. And there's 3 versions of this. It doesn't really matter which one you use. You got cosine of 2 alpha. I always remember this one, but the other 2 I have to just sort of figure out in my head. So that's going to be one form of that. Now, if I replaced the sine with 1 minus cosine squared, I would end up getting 2 cosine squared alpha minus 1. And if I replace cosine squared with 1 minus sine squared, I would get 1 minus 2 sine squared alpha. So actually it doesn't really matter which one you use. It's totally up to you. I think I'm just going to use the first one then. So I'm going to do the cosine of alpha. So if you go to our diagram, the cosine is x over r. So that's going to be 5 over the square root of 34 squared. Then we're going to do the sine of alpha, which is y over r. So that's going to be negative 3 over root 34 squared. And keep in mind, any of these 3 forms of this identity work. It's just take your pick. So you're going to end up then basically having, this is 5 squared is 25. Square the radical, that becomes 34. You have minus, and then negative 3 squared is 9 over 34 like that when you do that. All right, then when you do 25 minus 9, I think that is, it should give you the answer to that problem then after you reduce it. Okay, so that's going to give 16 over 34. Then we need to just divide that by 2 over 2, so that's going to be 8 over 17. Okay, so we got the answer to the sine of 2 alpha and the cosine of 2 alpha like this. Now I'm going to go down and we're going to look at the sine of 2 alpha, and I'm going to talk about the 2 different ways that you can actually do this. One way is a little quicker than the other one. I think most students, I do give this identity, I think most students probably would do it this way. So we have an identity for the tangent 2 alpha goes 2 tangent alpha over 1 minus tangent squared alpha, okay? Which is okay. Now, if you go back to the original problem, if you look at all the way up at the original problem, see, I gave you what the tangent is. I gave you up here that the tangent is negative 3/5. So I'm going to replace, in this expression, I'm going to have 2 times negative 3 over 5, I think is what I gave you. I already forgot. Yeah, negative 3/5. So I'm going to put that in like this, and in the denominator I'm going to go 1 minus negative 3/5 squared. So the numerator, you can put that over 1, and that will be negative 6/5. And then the denominator is going to be 1 minus 9 over 25. And what I would do, this is a complex fraction. The common denominator of 25 and 5 is 25. So I'm going to multiply the numerator by 25, and I'm going to do exactly the same thing to the denominator as I'm required to do, and then just work out the details. So I'm going to have 25 over 5 is 5. Negative 6 times 5 is going to be negative 30. The denominator, 25 times 1 is 25. Then when you multiply those out, you're going to get 9. So this is negative 30 over 16. Then you can divide this by 2 to get negative 15 over 8 as the answer to that problem. Okay? All right, so that's one way you could do this. If it were me, and it is me, this is how I'd do it. Okay? Seriously, I'd do it like this. If I was doing the tangent of 2 alpha and I already knew what the sine and cosine of 2 alpha is, I would just pull out this identity. This is the same as sine 2 alpha over cosine 2 alpha. So get your answers to part A and part B. Part A, the sine of 2 alpha is negative 15 over 17. Cosine of 2 alpha, part B, is 8 over 17. Look how cool this is. 17's cross out. You got the same answer. Negative 15 over 8, that saves you a little bit of time if you do it that way. Okay? Okay, now, kind of now getting into some identities and some simplification. One of the things that we're going to have going on this type of problem is just multiplying and using identities. Okay, so you need to be sure that you know all of your fundamental identities. So I'm going to start this problem. There's more than one way to do this. The way I'm going to start this is I'm just going to multiply it out. This is FOIL. So let's go ahead and let's do that. So the first term you would have sine cotangent times 1 is going to be sine beta cotangent beta. Then the outside terms is going to be sine cotangent cosine, positive times negative is negative. So I'm going to write that as sine beta cotangent beta cosine beta. Okay, then the inside term is 1 times 1 is 1. Then the outside term is negative cosine beta. Then I'm going to pull out some identities and see if I can simplify this. Generally, when you simplify, you want to get your expression to a point where maybe it just has one trig function and as few mathematical symbols as possible. So here's what I'm going to do. I'm going to use a fundamental identity there and there and see what happens. Okay, so what I'm going to do is I'm going to replace the cotangent with what it's equal to. That's equal to the cosine of beta over the sine of beta. Okay, that's just doing a basic substitution. Then I'm going to bring down the rest, and I'm going to replace the cotangent of beta again. I also have a cotangent of beta here. I'm going to do the same thing. I'm going to replace that with cosine beta over sine beta. And I'll have a few simplifications that occur when I do that. And let's see, bringing down the rest of this, this is going to be cosine beta. Then I have plus 1 minus cosine beta. All right, so let's see what happens here. Okay, so it looks like these cross out. These cross out. Let's write what we're left with. We are left with cosine beta minus, and then this is cosine squared beta now. and then you have a plus 1, and you have a minus cosine beta. Okay, it looks like these things will go to 0. So we're going to be left with this. Now I'm going to write this next step as 1 minus cosine squared beta. Now there is one more thing you can do. You have the fundamental identity that says sine squared beta plus cosine squared beta equals 1. So if I move that cosine there, notice I get sine squared beta equals 1 minus cosine squared beta. So that means I can replace this thing with this thing. All right, so that whole thing right there gets replaced with the answer to the problem, which would be the sine squared beta. Okay, that is as simple as you can get that expression. You got it down to one trig function, so that's where you would end the problem up. Okay, so that's a pretty straightforward example of simplifying a trig expression. You want to be able to do that. Okay, now we're going to get into some proofs. Now proofs I want to explain, and this is very important you pay attention to this. I won't grade proofs if I can't read them and can't follow your logic. There's really only one thing that's acceptable. When you're doing a proof, I want everybody to start the proof this way and don't do anything else. Write down the word proof. Okay? Pick a side, write it down. Usually you pick the side that looks like is the most complicated and might be the easiest to work with. So write down the left side, then put an equal sign. Do not start these problems any other way. That's how you start that. Now, there's a couple of identities that are going on this problem. But the thing that you want to know is we learned about odd functions and we learned about even functions. In trigonometry, the cosine and the secant are the only two even functions. They are symmetrical. Their graphs are symmetrical about the y-axis. And even functions go like this. You know, basically like if you had a point 2, -3, if you changed the x to a negative, the y would stay the same. All right, so that what this means is if you do the cosine of the opposite number, you're going to get the same thing back. Okay, and then you would also have the identity secant -x equals secant x. That's how even functions work. Everything else is odd. So like the sine and the cosecant, the tangent and the cotangent, they are all odd functions. And odd functions work like this. If you had this same point 2, -3, if you changed x to negative, then y would also go to opposite. So it's just opposite x, opposite y. So an example would be sine of -x, opposite x, opposite y. See, that's how it goes. So that's the structure of your odd identities like this. So what we're going to do is we're going to replace sine of -x with what it's equal to. That's equal to negative sine of x. Now the bottom, I think you would be wise to write this as cosine of -x, the whole thing squared. Now what we have is since the cosine is an even function, the cosine of -x is going to be cosine of x. So your next step you'd write on your proof is you would say negative sine x over cosine of x to the second power. Now keep writing your equal signs. Draw a little arrow to show where you're going if you need more room on your paper. So I'm going to write this as negative sine x over cosine squared x. We're trying to prove that it's a tangent secant. So the best way to me to show this is just break this up into two parts. Put this as sine over cosine x times 1 over cosine x. Okay. Then this is the tangent, and then this is the secant. So we're done. Okay, so you replace sine over x with tangent because you have an identity that says so. 1 over cosine is the secant, and then you have proved it. Now that's a really nice, elegant mathematical proof. You wrote a side, equal signs, substituted equals for equals. Ultimately, your job is to write a side down and then show that it ends up being the same as the right side. That's it. I don't want your proofs to look any other way. I don't want you to write sideways, sloppy scratch work all over the paper. I don't want you to lose your equal signs. I don't want you to lose your variables. I take off if you don't have your proof exactly right. Okay. There are a few steps that I could allow you to skip in your head. Okay, that's a judgment call, but you got to have this structure. Okay, so let's do another proof here. Okay, this one actually turns out to be pretty simple. I think most of the proofs that I give on tests, because of time pressure, are not real advanced proofs, just kind of easy to moderate level proofs. Okay, so again, we're going to start this the same way. Write the word proof, pick a side, write it down. Okay, so to me, it's very clear on this problem that the left side's a heck of a lot more complicated than the right side, so write it down and then put an equal sign. Okay, I'll say it again, do not start your proofs any other way. Okay, I want this proof to begin that way. Now, it's just identities. Think about whatever identities you want to use. There are many ways to do proofs. Okay, I'm going to use identities for those two things right there that I just highlighted. Okay, so I'm going to replace the tangent with what it's equal to. That is equal to the sine squared theta over the cosine squared theta, while I leave the cosine alone. Okay, then I'm going to go over here. I'm going to replace the cotangent with what it's equal to. It's equal to the cosine squared theta over the sine squared theta. Then I'm going to leave the sine alone. And this is a real simple proof. So what happens is those divide out. Write what you're left with. You are left with sine squared theta plus cosine squared theta, and we know that we have an identity that says sine squared theta plus cosine squared theta equals 1. Real simple proof, and again, the idea is you wrote a side, never lost those equal signs, and you ended up with your other side. That's how proofs are supposed to look. Okay, next problem, same way, start it the same way. Write the word proof, pick a side. It's probably a lot easier on this particular problem to start this way. I think you could go either direction. I like this way. It looks a little bit more complicated to me. Write it down, write an equal sign. Okay? Now what you have on this is we have identities. We have a sine sum identity and we have a sine difference identity. So I'm just going to write them down, excuse me, and then I'll see what happens. Okay? So the sine sum identity goes like this. It's going to go sine alpha, cosine beta, no, yes, same side, cosine alpha, sine beta, so it's going to go like that. Then you have your plus sign, okay? That's going to go like this. The difference identity is going to go sine alpha, cosine beta, same sign, then cosine alpha, times sine beta. Okay, so you do that and get everything written down. All right. So now what we're going to have is, let's see what we got here. I think we might have something that cancels out. It looks to me like this, cosine alpha, sine beta. Those things cross out. And then what we're left with looks like like terms. This is sine cosine, sine cosine. So there are two of those. So this is a real simple proof. It just takes like 2 steps and you're done. Okay? Okay, let's see. Now on the next page, we're going to talk a little bit about what we mean by cofunctions. Let me pause this for a second. Okay, so let's take a look at cofunctions now. So the first thing is, what are cofunctions? Well, okay, we have, it's easy to remember, of course, the sine and the cosine are cofunctions. The tangent and the cotangent are cofunctions. The secant and the cosecant, okay, go together, they're cofunctions, okay? So, and what it means is the angle's got to be complementary. So the thing that we learned was, like, if you took a trig function, and say that's like 10 degrees, that will be the same as the cofunction of the complement. The complement's always found by subtracting from 90. So that would be cosine of 80. So we would know that the sine of 10 and the cosine of 80 are the same. So the sine and cosine of complements are equal. The tangent and cotangent of complements are equal. And the secant and cosecant of complements are equal. So it's very simple to do this. You don't want to mess up on this. This is just knowledge level stuff. Okay, so if I give you the cotangent of 23 degrees, and I want you to write this as a cofunction, okay, well, you do the tangent of the complement. So your job is to do 90 minus 23 degrees. So that's going to be, let's see, 90 minus 20 is 70. So this should be tangent of 67 degrees. And make sure, I mean, don't make any mistakes on this. I mean, you know, if you do 67 plus 23, well, you're going to get 90. I mean, the two angles have to add up to 90 because that's what complements are. The next one's radian measure. So if I give you the sine of 4 pi over 5, okay, the cofunction of the sine is the cosine. Subtract it from pi over 2, because pi over 2 is the same as 90 degrees, but we want to work with radian measure on this problem. Okay, common denominator between 2 and 5 is 10, so that means this needs to be multiplied by 5 over 5. This needs to be multiplied by 2 over 2. So what you're going to get is the cosine of 5 pi over 10 minus 8 pi over 10, I think. And that's going to be the cosine of negative 3 pi over 10. And it's fine if you get a negative answer. There's not a thing wrong with that. So that would be your solution to your problem. Just be sure that you have everything simplified. Okay, now we're going to look at a half angle identity. Now again, I will be kind enough to give you the half angle identity. So the half angle identity for a cosine goes like this. The cosine of an angle over 2, half of the angle, is equal to plus or minus the square root of 1 plus cosine alpha all over 2. Your job on this problem is to take the angle I gave you and double it. And that's the first thing you got to do. So you got to be able to do this arithmetic right without a calculator. So 2 times 5 is 10, carry that. 14 plus 1 is 15, carry. 10 plus 1 is 11, carry. 315 degrees. If you don't like multiplying, then just add it to itself. Okay? So what we're going to work with is we're going to work with the cosine of 157.5 degrees being the same thing as the cosine of 315 over 2. Okay, a couple of things to note on this. Okay, this is a quadrant 2 angle. The cosine of a quadrant 2 angle is negative. So that means that you have to conclude that you're going to use that negative symbol right there. Okay, and then when we plug this in, we're going to have negative square root, and then do exactly what the identity tells you to do. The identity says do the cosine of alpha. Alpha is 315. Alpha is not 157.5. Okay, then plug it in and then work out the details. So you're going to have 1 plus cosine of 315 degrees all over 2. Okay, go to a unit circle now if you need to, and I'll just put a little diagram at the side on this. Okay, 315 degrees clearly is in quadrant 4. And on the unit circle, that corresponds to the point positive square root of 2 over 2, negative square root of 2 over 2, like that. So the cosine of 315 degrees will be positive square root of 2 over 2. So what we're going to have is negative square root of 1 plus square root of 2 over 2 all over 2. And we've got a complex fraction, so we're going to get rid of that by multiplying by 2 over 2. Okay, so what we're going to have is, in the numerator, we're going to have a big radical again here. So 2 times 1 is 2. These cross out. Remember, you're doing a distributive property. And then 2 times 2 is 4. And then you can do the square root. Now, you don't necessarily have to show this step. But what you have is this really. Okay, and then, of course, the square root of 4 is 2. So you can just replace that with 2. And then the problem's done. Okay, so that would be the final answer of that problem in like that. All right? Okay, a couple of things to move on. Of course, odd and even identities will be something you're kind of tested over here and there. Okay, first of all, the cosine is an even identity, is an even function. When you have an even function, what it means is if x is opposite, y stays the same. See, this doesn't change. That started plus, it ended up plus. So that's cosine of x. The sine is an odd function. Odd functions work like this. When you change the x to negative, the value of the sine goes to opposite. So you get sine x. So see, the thing is, opposite x, opposite y. So that's going to be negative sine x. Okay, and then the next one, a cotangent, is also an odd function. So this one goes like this. I'm going to write this as negative cotangent of negative x. Okay, well, since it's an odd function, this part right here becomes opposite. So cotangent of negative x is negative cotangent of x. Then you have two negatives that are going to multiply out to give a positive. So the answer to that problem is cotangent of x. Okay, next problem is a proof. There's one more proof. This one's actually pretty easy too. So again, we're going to start this like this. We're going to work with write proof, pick a side. It's probably a little simpler to work with the left side on this one. So write it down, write an equal sign. Now what we're going to do is we're going to multiply this out. Okay, this looks like you just need to do multiplication, do FOIL, distributive property. Like that. Okay, FOIL it out, you do it in your head. First term, sine times sine, is sine squared x. Outside term is negative sine x cosine x. Inside term is another negative sine x cosine x. And then last term is positive cosine squared x. Okay. All right, so what I'm going to do is I'm going to rearrange things a little bit. You could actually bypass this step if you wanted to, and I wouldn't fuss at you. I'm going to put those together, and then these are like terms, so that's minus 2 sine x cosine x, because those are like terms. Okay. So what I end up with, of course, is this is 1. That's an identity. Minus 2 sine x cosine x. That's what we're trying to prove. Okay. Now, the other thing you got to see is you would have to know that 2 sine x cosine x is the same as sine of 2x. Okay, so you just now get 1 minus sine of 2x. Okay, so that's the proof. Again, you wrote a side. You wrote equal signs, you did equals for equals, you got the result. That is perfect proof. Okay, let's see. We've talked about this several times. So a lot of times I just ask the question, what are the even functions, what are the odd functions? The even functions are the cosine and the secant, and everything else is odd. So the sine, the cosecant, the tangent, and the cotangent are all examples of even functions then. And that'll take care of that. All right, I'm going to pause this for a minute, and then the rest of this is going to be talking about graphing. Okay. All right, now we're going to get into the graphing part of this. And to begin with this is I want to just be able to take a basic function, a cosine or a sine, and be able to tell all the different parts of the transformations. First thing I want to mention on this is this particular expression is not in a factored form, and you need to make sure it's in a factored form to help you to determine that phase shift. So you got to pull that 3 out. And you need to write this as 5/6 times the cosine, and then draw a bracket, 3 with a parenthesis, and then 7/3. So you want to be sure that you're solid on that factoring when you do this. Okay, so the amplitude is, what we said is the amplitude is just this value, okay? And it's always a positive number, so don't ever put a negative answer for that. So the amplitude is going to be 5/6, okay? That's the value of A. Okay, the phase shift is this number. Okay, and it gets the factored form, and that's going to be a phase shift to the left. Okay, so that is a left phase shift. I'll go ahead and fill out the answer to that problem. And since it's left, we usually do negative 7/3 for that value. Okay, and then the period, we have a formula. Whenever you're dealing with a sine or cosine, it's 2 pi over absolute value of b, and the b value is the coefficient of x. Okay, so that's going to mean the period is going to be 2 pi over 3. Okay, now vertical translation is this number. Okay, so this number right here is telling you that you're going up. So that is an up transformation of 8.9. So a real basic thing you want to be able to do is given a sine or cosine or any of the trig functions, be able to know the amplitude, phase shift, period, translations, and all that kind of stuff. Okay. Moving to the next page. Okay, what we want to look at on this is we want to do a couple of graphs. So you want to be able to do graphs of sines and cosines to start with here. Okay, so to begin with this one, I'm just going to make a table of values on this. So I'm saying graph over one period. Now this one, anytime that you just have a sine of x, if you have nothing in front of that, or a cosine of x, you have nothing in front of x, that means that the period is equal to 2 pi. So you got to know that. And then when you do the increment of the x-axis, you always take the period and you divide it by 4. So pi over 2 is going to be how you increment this. So I'm just going to start at 0. There's no phase shift or anything. So let's just start at 0. And let's count out by this increment. Pi over 2, then we'd go 2 pi over 2, which is pi. Then 3 pi over 2. And eventually we'd get up to 4 pi over 2, which is 2 pi like that then. Okay. Then what we're going to do is just work out the details of this. So basically, one of the things that's real helpful that you remember on these problems, I'm going to go ahead and go down to my graph and go ahead and start kind of piecing this thing together. And we're only going to graph this over one period, so let's get everything worked out. We got pi over 2, we got pi, we got 3 pi over 2, and then we got 2 pi. Now what I'm going to do on this, on this problem, just kind of to remind you of something, let's just do the graph of y equals sine x. If you get the graph of y equals sine x memorized, it'll make this problem go pretty smooth. So now the graph of the sine x has a maximum of 1 and a minimum of -1. So I'm just going to do this graph in maybe in a dashed line like this. So just remember the sine starts at 0, 0. So we got that. Then it hits its high point, and then it's back to what we call the midpoint. Then its minimum point, and then back to the end point. So those are the 5 key points on a sine wave like that. Now this particular problem has just a couple of transformations to it. So if you were going to just look at these y values, at 0 you have a y value of 0. Then you have a y value of 1, 0, -1, and back to 0. Now what's happening is this value right here is really, it's multiplying y by -5. So I'm going to take these y values, and I'm going to multiply them by -5. So that's going to be 0. This is going to be -5. This is going to be 0. This is going to be +5. And this is going to be 0. So now we just plot these key points, and then we've got a good graph. And it'll have the reflection and the stretch and amplitude change and all that. Okay? So I'm going to take this up to 2, 3, 4, 5, and down to 2, 3, 4, -5, and just plot the points from that table of values. And this is the simplest way in my mind to get this done. Okay, so let's plot our points, and then we'll be finished with it here. Okay, so we got a point 0, 0 here. Okay, this point moved up to -5, sorry, because we had that reflection. This point stayed where it was, still has a y value of 0. This point went all the way up to 5. It did have a reflection and a vertical stretch, then back to 0. So then just sketch it in, just connect the dots into curves, kind of like this, and then that'll take you through one period. So the solid graph would be the graph of y equals negative 5 sine x. So this is kind of a basic reflection and vertical stretch thing like that. Okay. Okay, now we're going to do a cosine. And this one's got two different transformations on it. The very first thing, excuse me, that you need to notice on this is you're dealing with y equals cosine of 1/2 x. There's two things going on. This is basically a down 3 transformation, and then this is a period change. So the period, the formula for the period is 2 pi over b, and b is 1/2, so we're going to say 2 pi divided by, whoops, not 2b, 2 pi. So we're going to say for the period, we're going to get 2 pi divided by 1/2. So that's going to be 2 pi times 2 over 1, so that's 4 pi. Now you got to go to the increment of the x-axis. Okay, the increment's always the same. It's very important. Take the period, divide it by 4. That'll give you pi. So what that's going to mean is on our graph, if we're going to graph this through one period, we need to increment this by pi on the x-axis. Okay, so I'm just going to start here, count by pi. 1 pi, 2 pi, 3 pi, 4 pi. Okay, and then that'll take us to the end of the period like that. Okay, this thing has an amplitude of 1, but we are going to be moving everything down 3, so our y value needs to go down from a minimum of -1 to a minimum of -4. So I'm going to go like this, 1, 2, 3, -4, then up 1, 2, 3, 4 like this, and then get this put together. All right, so what I'm going to do is I'm going to go ahead and just do this in 2 stages. You're not required to do this. But stage 1 is going to be, just consider the this part right here, and then we'll switch all those points down 3 like that, excuse me. All right, so I'm going to go ahead and do this in red. So remember, a cosine starts high. Okay, so it goes there, and then it just sort of cycles through these key points. This is, we don't have an amplitude change. We're going to do this as a step before we do the vertical translation. Okay, so I'll do this in dashes to just kind of remind myself that this is not the final result on this. It's just the beginning. Okay, now what we're going to do is the final is we're going to take this and we're going to take all those y values and we're going to move all of them down 3. Okay, so just take this one, 1, 2, 3 down, that gives your new point. This one down 3, new point. This one down 3, new point, and so forth. Okay, this one would go down to -2. Then you can plot that out, and you got what the graph looks like. Okay, now another thing I want to mention on this, and you know, when you're dealing with a test and everything counts, is you might as well check your answer. And what you can do on this is you can pick any point you want to. We just got through graphing 1/2 x minus 3. And just keep it simple. I'm going to check 2 pi. So I'm going to plug that in. And I should get a y value of -4. Okay, that y value is -4. So notice the 2's cross out. That's really why I chose that. So we'd have cosine of pi minus 3. Okay, well, the cosine of pi is the x value, so that's -1. So -1 minus 3 is -4. That checks. That's all you got to do. I mean, you can check all 5 points if you want to, but if you at least just check 1 point or 2 points, and you're pretty confident you've done it right. That's all there is to it. Okay, now this number 18 on this page, this is a little bit more complicated. It's got more going on. So one of the things that we want to go ahead and work with on this one is finding all the parts of this. So the first thing is the period on part A is 2 pi over b. Okay, well, b in this problem is 4. So that's going to be 2 pi over 4. So the period is going to be pi over 2. Okay, now while we're at this, let's just go ahead and get everything put together. So the phase shift, now see, this is in a factored form. So that's your phase shift. So that's going to be 3 pi over 8. It's going to be to the right. So we just put 3 pi over 8. But let's make a note to ourselves that we're going to the right. Okay, because of the minus sign. Okay, the amplitude is, excuse me, the number in front of sine, which is 1. Okay, remember, amplitude and period are always positive numbers. Then the vertical translation is going to be that you're going up 2. Okay? Now, on your part E of this, you're doing the increment of the x-axis is always the period divided by 4. So the period is pi over 2. Now, when you divide by 4, you're really multiplying by a fourth, so you get pi over 8. So that's going to tell you, when we make this table out, we want to count by pi over 8. Now, what I want you to do on this, my directions of this problem say start at the phase shift. So we're going to start at 3 pi over 8, and then we're going to count up by pi over 8. So we're going to go 3 pi over 8. You can actually just kind of start this way if you want to. 0 pi over 8, 2 pi over 8, 3 pi over 8, 4 pi over 8, and so forth. 5 pi over 8, 6 pi over 8, 7 pi over 8, and so forth like that. So I'm going to go 3 pi over 8. This is really pi over 2. Then 5 pi over 8. 6 pi over 8 is really 3 pi over 4. And then 7 pi over 8 like that. So that'll get us to the end of one period. And we'll fill out this table of values, and I'll show you how to do that then. Okay, so I'm going to go down to my graph, and I'm going to go ahead and get the increments. Now, don't start at 3 pi over 8. I mean, count it out like this. I just want the graph to go from the phase shift through one period. So let's, mark this off like this. You got pi over 8. You got pi over 4. You got 3 pi over 8. 4 pi over 8, which is pi over 2. 5 pi over 8. 6 pi over 8, which is 3 pi over 4. Then all the way to 7 pi over 8. Now, if you wanted to go to 8 pi over 8 and go to pi, you can do that also. And a couple of things to notice on this. You have an amplitude of 1. And then you got an up 2. So that means you probably need to move this thing up to about 3. And we'll just go down to -3 like that. And we should have enough room to do everything. Okay? Now, what I like to show students to do on this is just do this in 2 or 3 steps. It's up to you. Really, what you kind of work with is you work with phase shifts and period changes, and then you would do an amplitude and an up 2. So really all we need to do on this is we could actually just right now graph in red y equals the sine of 4 times x minus 3 pi over 8, and not even do the 2. Okay, we'll do this in 2 steps. All right. So here's kind of the way I look at this is like this. Now, by doing this x-axis, by changing this x-axis, see, we've dealt with the period change by these increments. Okay, now a sine wave typically starts there. We know the first point on a basic sine wave is 0, 0. We're going to phase shift this to the right 3 pi over 8. Okay, so this point is going to move right there. Okay, now in your mind, just think, well, how does the sine go? Okay, this point goes there, this point phase shifts to here, and so forth. Okay, like that. Then you can begin to cycle through these points through one period like that. And all I'm going to do is, we got 5 key points. That'll be good enough. You can go further if you want to, but you don't have to. Okay, now what we're going to do is we're just going to take every point and we're going to move it up to, and then we'll have the final result of this problem. Okay, so this one's going to go up to that point. This one's going to go from 1 to 3. This one's going to go up to from 0 to 2. This one goes -1 up to 1. This one goes up to 2. And then you've got your graph right there. Okay, it's all done. Okay. Now, I can't emphasize enough when you're doing these problems, the ability to check is really good. I mean, you can go ahead and fill your table of values out now. So 3 pi over 8, you got 2. Pi over 2, you're at 3. What in the world did I do? Okay, so at pi over 2, you've got 3. 5 pi over 8, you're 2. 3 pi over 4, 1. 7 pi over 8, 2, like that. Okay, so you've got those values on there now. Now, if you want to check, just pick one. Now, and my thing is I always try to keep it easy. If you plugged 3 pi over 8 in, it would make it real easy to check. So let's do this. Let's do y equals sine of 4 parentheses 3 pi over 8 minus 3 pi over 8 plus 2. You can pick anything you want to, but I sure like 3 pi over 8 because it makes it easy. So you're going to end up with y equals the sine of 4 times 0 plus 2. So that's the sine of 0 plus 2. Well, the sine of 0 is 0. 0 plus 2 is 2. Look at that. It checked. That has a y value of 2. That's it. Okay, I mean, if you learn to do that, you'll understand this stuff so much better. All right, so that'll take care of that. Let's go to the next page. And now what we're going to look at is the graphs of the tangents, cotangents, secants, and cosecants to kind of finish this up here. Okay, so one thing I want to do is I'm going over this graph is I want to remind you, and I think this is pretty important as we're reviewing this, as how a basic tangent graph goes, okay, before we do anything. So basically what happens on a unit circle, if you look at a unit circle, I'm going to just sort of redraw a unit circle to just sort of show you what my thought process is on this. Is first of all, one of the things we learned is we learned the period of a tangent or a cotangent is just pi. Okay, so if we did the increment, we always take the period over 4. So when we construct a graph on a tangent, we're going to go 1 pi over 4, 2 pi over 4, 3 pi over 4, pi, and so forth, like that. And then you can do the negative ones like S. And I'm just going to show you enough information. If you have this memorized, you'll work your problems out a lot faster, because tangents and cotangents tend to be the graphs that students struggle with the most. So I want to go through this pretty thoroughly. If you were to look at a unit circle, if you look at 0 radians, you got the point 1, 0. The tangent's y over x. So that means 0 over 1 is going to be 0. So you're going to have the tangent of 0 is going to be 0. Okay, if you go to pi over 4, which is 45 degrees, you're looking at the point on the unit circle, root 2 over 2, root 2 over 2. Tangent's y over x, so that's 1. So you're going to have a point of 1 like that. If you go to pi over 2, you're looking at the point 0, 1. Y over x in this case is undefined. So remember, we had a vertical asymptote at that point like that. Then if we were going to go to negative pi over 4 is clockwise this point, which is root 2 over 2, negative root 2 over 2. The tangent's y over x, so that's going to be negative 1. And then if you look at negative pi over 2, that's a point 0, negative 1. Y over x is undefined, so you have an asymptote. So if you get this memorized, or at least be able to figure it out, then this is how one period of the tangent graph would go, is kind of like that. You have the asymptotes. So what we're going to do on this is, well, we got a couple of things on this. The period, there is nothing in front of x. That's just 1x, so the period's pi. Okay, and then that would mean that the increment, which I already did in the table, is pi over 4. Okay, so we got that. Now, the vertical asymptotes, we'll talk about that in a minute here. So the first thing we're going to do is we're going to fill in this table going from 0, counting by that increment up to pi, and then we're going to graph this. So the first thing that I like to get students to do on these kind of problems is find asymptotes. Find your vertical asymptotes. So there's actually two places on a unit circle where the tangent's undefined. One place is pi over 2. The other place is negative pi over 2, or you can even use 3 pi over 2 if you want to. It doesn't make any difference. So we're going to do this. We're just going to, we already know that since there's no period change, that we're going to be undefined right there. Pi over 2, we're undefined. Okay, so we're going to do that. Now what we're going to do is, if you look at 3 pi over 4, or even if we go to pi over 4, the tangent had a value of 1. And then at 0, the tangent had a value of 0. If we went further out on this, 3 pi over 4 would have a y value of negative 1, and pi would have 0. Now, all we're doing on this problem is we're translating this graph, so we're doing two things. We're going to multiply these y values by half, then we're going to add 3 to it. So we're going to do this to each one of these things. A half times the y value plus 3. A half times the y value plus 3. And so forth, and then we'll have everything transformed. Okay, like this. All right, do what you can in your head then. So this is going to be 0 plus 3, or 3. This is 1/2 plus 3, so it's 3.5. The asymptote's not affected. This is negative 1/2 plus 3, so it's 2.5. That's 0 plus 3, so that's 3. Now we're ready to go through and do a graph, okay? So what we're going to do is just kind of go up to pi on this. So let's just write this as pi over 4, pi over 2, 3 pi over 4, and pi, like that. And we need to go up to at least 3. And down a ways like this. Now let's just plot the points. So what we have is we had an asymptote here. So we're going to do an asymptote at pi over 2. Okay. We have a point 0, 3. We have a point pi over 4, 3.5. So this part of the graph is going to be doing this and approaching the asymptote. 3 pi over 4, we have a point 2.5. And pi, we have 3. Okay, so we can make this sort of approach like that. And that gives the graph. Now you can go out further on that if you want to. So I'm going to take this out just a little further, although you're not required to on this problem. This would be 5 pi over 4, 6 pi over 4, which would be out to 3 pi over 2. So if you did this same logic, say if you count to 5, you'll get another asymptote. So 5 key points, 1, 2, 3, 4, 5. So you're going to have another asymptote there. And then by the same logic, this point's going to go up to, this is up 3, so it's going to go up 3.5. Then you would have like 1 period there, okay? And that's it. Now we'll go back and do the equations of the asymptotes next here. So if you look at your vertical asymptotes, just go through and look at a pattern. We have pi over 2, 3 pi over 2. And you can predict from this information how they're going to go. So you have pi over 2, 3 pi over 2. The next one's going to be 5 pi over 2. And then 7 pi over 2 and so forth. If you just keep counting, you're going to 5, you're going to get that over and over again. So it's just going to go 1, 2, 3, 4, 5, and then continue to go through that pattern like this. So you could say x equals k pi over 2. And what k is it's this number. Pi over 2 is always built into the equation. So those are odd integers. So one way that you could write this out is you could say x equals k pi over 2 with k, where k is an odd integer. And I would be okay if you wrote it that way. The other thing we learned, as I said, you can use a formula. You can say x equals just whatever vertical asymptote you want to use, typically the first positive one, plus the period times k, where k is an integer. So you can use this formula if you want to. It always works. So what you could say is x equals, well, here's an asymptote at pi over 2. The period of this thing when we worked this out was pi times k, with k being an integer. So actually, either of these two answers is okay. You can write it this way, or you can write it that way. They're both the same. Mathematically, they're equivalent, and they're going to generate those answers, okay, like that. Now, one other thing I want to do on this is do a check. So it's a good idea to just, pick a point. You're checking 1/2 tangent of x plus 3 So again, what we're doing with this is just pick any point you want to. It doesn't matter. Let's pick pi. Why not? So let's do 1/2 tangent of pi plus 3. Okay, if you went to a unit circle and looked at pi, you're at the point -1, 0. So y over x is 0 over -1, so it's 0. So you have 1 times 0 plus 3 is 3. Well, notice, that's what the y value is. Okay, that has a y value of 3. Or you can look at my chart up here at pi, you got 3. That checks and verifies that you have a right answer. Okay. Okay, let's do a cotangent. Okay, now on a cotangent, one of the things you want to look at is finding the period and all those parts of this. Let me make sure I got all the parts of the last problem before I move on. So, yeah, I think I got everything here. So I gave the vertical asymptote and everything, so we're good. Okay. All right, so on this one, the formula for the period is pi over b on a cotangent. So this is going to be pi over pi. Again, pi is the coefficient of x. And a lot of times students just freak out when the pi's cross out. I like it when the period's 1. It makes the problem easier. Okay. Now, we don't have an amplitude. That's another thing. Don't fall for that. Okay, cotangents graphs look like this. They don't have a max, they don't have a min, and you have to have a max and a min in order to have an amplitude. The only things that have maxes and mins are sine and cosine. Okay, so I always ask that just to make sure you're paying attention. Okay, all right, now the increment is always the same, so what you're going to do on your increment is you're going to take the period, and you're going to divide that by 4, so the period's 1. Divide that by 4th, you got 1/4. Now we're going to make a table of values starting with 0. I state that in the problem. So we're going to go 0 and we're going to count by 1/4. So we have 1/4, 2/4, 3/4, 4/4. And then of course just reduce these two fractions like that. Okay, so one of the first things you want to do is if you were to go through and look at a unit circle, just kind of as a point of reference here, on a unit circle, we want to figure out kind of, where on a basic unit circle is the cotangent undefined. Well, the cotangent's x over y. So one thing you would find is at 0 radians, you would have 1 over 0, so you're undefined at 0. The other place you're undefined is at pi, because you have the point -1, 0, so that's undefined. So what you do, if you want to find asymptotes on a cotangent, you can set the argument equal to 0 to get 1. Then you can set the argument equal to pi to get another one. Now the argument is this thing right here. It's the whole thing. So it's what you're taking the cotangent of. So you could say pi x equals 0, solve that equation. Then you could say pi x equals pi and solve that equation. Then you got your asymptotes. So this one, if you divide both sides by pi, well, you're going to get x equals 0 is an asymptote. So we know that we're undefined there. Okay, take this one, divide by pi. You get x equals 1. So we know when x is equal to 1, we have an asymptote, like that. Okay, now we also have this thing, that -2. What that's going to do is it's going to multiply all the y values on a basic cotangent by -2. Okay, so if you went through and looked at a basic cotangent graph, I'm just going to review for you real quick how a basic cotangent graph goes before we construct this final graph. What we learned on a cotangent graph is you go pi over 4, pi over 2, 3 pi over 4, and pi, and then you can go with the negatives like this. Okay, I'm just going to write that. Well, we have an asymptote at pi. That's one of the places where the cotangent's undefined. We have an asymptote at x equals 0. That's another place where you're undefined. And if you went to negative pi, you would also be undefined. Okay, then the tangent graph, or the cotangent graph, went like this. Halfway between the asymptotes, y value is 0. And this is 1 there, -1 there, and the graph goes like that. Okay, same thing here. Halfway in the asymptotes. It's real easy to remember how those points go. That's what a basic cotangent of x graph goes, is like that. So the y values go like this. Okay, halfway between your asymptotes, 0, to the right of that, -1, to the left of that, 1. But what we're doing is we're doing a transformation of -2. So we're going to multiply these y values by that -2. Okay, so what that's going to give is that's going to be -2, 0, and 2. Okay, now we're ready to sketch our graph. Okay, so on the x-axis, we're going to go 1/4, 1/2, 3/4, and 1. For the y-axis, let's go up to 5 or something like that, and that's probably good enough. -5 to 5. And let's plot our points. Okay, so the first thing we have is we have an asymptote. We said we had an asymptote at 1. So we're going to go ahead and sketch that in with a dashed line. We also said we had a vertical asymptote at 0, or the y-axis, like that. Then just plot your points. 1/4, -2 is a point. 1/2, 0 is a point. 3/4, 2 is a point. Sketch it in. So you've kind of stretched the cotangent graph vertically, and you also reflected it. So that's it. Okay, now if you look at your asymptotes, the vertical asymptotes on this problem kind of go like this. We have vertical asymptote at 0, 1, and then you can, same logic, 2, 3, so forth, and then -1, stuff like that. Well, there's no pi in it, but what these numbers are is they're all integers. So you could just say x equals k, with k being an integer. Okay, and then that would be a good equation of the vertical asymptotes like that. Okay, the formula is x equals a vertical asymptote plus period times k. Well, we have an asymptote at 0, so we could just say x equals 0 plus the period. The period's 1 times k, and you could say k is an integer. Well, that gives exactly the same thing as this. They're the same thing. Okay, so that would be an answer to that problem like that. Okay, so we'll just say for our vertical asymptotes, I'll go up here and let's just write this like this. It's x equals k, where k is an integer. Okay, and then that problem's done. Okay, now let's move on and let's do a secant graph I want to go through and look at next here. And you'd also want to know how to do a cosecant graph. Okay, so the first thing we're going to do on this is just identify everything. The period comes from this number, whatever the coefficient of x is. On a secant, the formula is the period is 2 pi over b. So we're going to have 2 pi divided by 1/2. So that's 2 pi times 2 over 1. So that means we have a period of 4 pi. The increment is the period over 4. So we're going to have an increment of pi. The amplitude, we do not have one. Don't fall for that. Okay, the amplitude of the cosine is 4, but the secant does not have a max or min, therefore it doesn't have a amplitude. And then the phase shift, this isn't a factored form, is -pi, and that's going to go to the left. Now what we're going to do on this problem, first of all, is we're going to graph out, in a dashed line, we're going to graph out just this part of the problem right here, just this part. Not going to worry about that 4 or that -1. We're just going to worry about that part right there. That's the way I always teach these. So we're going to look at y equals cosine of 1/2 times x plus pi, and just look at that. Okay? And then we'll worry about the 4 and the -1 in the second step. Okay? And you could also do the 4 in this step too if you want to, like that. All right, so the increment is pi. So the first thing we need to do is we need to go ahead and just do the x-axis by pi's. So let's go pi, 2 pi, 3 pi, go out as far as you want, 4 pi, 5 pi, like this. Now, I think all I wanted was 1 period. It doesn't matter what those 5 key points are, as long as they're correct. Okay, so I'm going to take this out maybe through a couple of periods, although you wouldn't have to on this. Okay, the other thing is, in the graph that we're doing, you're going to have amplitude on the cosine goes up to 4 and then down 1. So you're going to have to make your y-axis go up at least to maybe 5 or something. So I'm going to go ahead and get this put together. Okay, like that. Okay, so we're ready to go. Now what we're going to do is we're going to look at this graph right here. Just this. All right, now you always want to start at the phase shift. Okay, a cosine, a basic cosine starts at the point 0, 1. Phase shift that to there. Okay, put a dot there. Okay, I hate it when it does that. Put a dot there. Okay, now the second point on a cosine is here. That phase shifts to there. Now you see the pattern. You're going to be maximum, midpoint, minimum, midpoint, maximum, midpoint, minimum. Okay, like that. And then you can just sketch that through with a dashed line. Like that. And you could continue to go as far on this as you wanted to. I mean, I'm just going to keep going on this just because I feel like it. So that'll take care of that information right there. And that's it. See, the thing is, the increment took care of the period change. And then we just started at the phase shift of a cosine like that. Now that means when we put this all together, we're going to be looking at y equals, I think we had a vertical stretch. So we're going to be looking at 4 cosine 1/2 x plus pi minus 1. Now, if you could handle this all in one step, that's fine. I'm just going to take every point. Let's just start here. You're going to multiply by 4 and subtract 1. So this y value is 0. So 4 times 0 minus 1 is -1. That point goes there. Okay, that takes care of that. Now this point has a y value of -1. So you're going to go 4 times -1 minus 1. That's going to take that point all the way down to -5. This point has a y value of 0, so it's going to be the same as the previous point. This has a y value of 1, so you're going to go 4 times 1 minus 1, which is 3. Okay, so that point moves from 1 up to 3, like this. And see, basically you've gone through, and you can continue to cycle through as many of these points as you want to. Okay, like that. Okay, and then this point right here would move down to -5 and so forth like that. So that's it, okay? And I'm just going to work with that because all I want to do is a period of this anyway. So the asymptotes always occur where these midpoints are. So you're going to go ahead on this and you're going to draw a vertical asymptote through -4 pi. You're going to draw another vertical asymptote through 2 pi. Like this, and then every 2 pi you're going to keep having asymptotes over and over again like this. Okay, that's just a matter of sketching. So you're going to have the upwards U shape there, a little part like that, and a little part like that. Now that's over more than 2 periods. You could graph as far as you wanted to on this. Now when you're starting to write your equations for the vertical asymptotes, again, you can look for a pattern. So the pattern goes like this. It's looking like what we have is 0, 2 pi, 4 pi, so you can conclude that it's going to go 6 pi, 8 pi, even pi's. So you could say x equals k pi, where k is an even integer. So if you see the pattern, you can do it like that. The other thing that you can do is I gave you a formula that says, and this is for a secant or cosecant, it's x equals vertical asymptote plus 1/2 the period times k, where k is an integer. I don't give you that formula, but you can memorize it if you want to. So you have an asymptote at 0. So you could say x equals 0 plus half the period. The period on this was 4 pi times k, with k being an integer. So you could write this as x equals 0 plus 2 pi, or just 2 pi k, where k is an integer. So that would also be a valid answer. So you could either give me this answer just looking at the pattern or by using the formula. Okay, problem done. And this problem can also be checked, which I think I'll do on this problem just to show you this, because this is one last good thing to do. So we just got through graphing y equals 4 secant of 1/2 x plus pi minus 1. Hey, let's use negative pi because it's easy. Okay? Or actually, why don't we use pi? Let's use pi, just use this point right here. Positive pi. That's also easy. So we got 4 secant 1/2 pi plus pi minus 1. Well, that is 4 times the secant of 1/2 of 2 pi minus 1. So that is going to be 4 secant of pi minus 1. Well, on a unit circle at pi, you're at the point -1, 0. The secant is r over x. So that'd be 1 over -1 or -1. So you have 4 times -1 minus 1 is -5. So notice that that y value is -5, so it checks. Okay. Okay, so that should be the end of it. Now, I just wanted to say, these are the only things I give you on this test. It's totally non-calculator. I give you these identities and these identities. Everything else, every other identity we've learned, your job is to know them. That's life. Higher math, you got to know identities. You just do. You don't want to be looking up stuff all the time. Okay, so that will take us through that. It's a pretty long presentation. Lots of stuff to study, so good luck with your test. Study hard.